Welcome to another example of the applications of extrema of functions of two variables. The goal of this video is to maximize the volume of a box bounded by a plane. So here's the problem. We want to determine the dimensions of a box in the first octant with the maximum volume having one corner at the origin and one corner lying on the plane x plus 3y plus 4z is equal to 12. So if you were to visualize a point on this plane, we would be able to construct a box where one corner was at this origin and one of the upper corners would be bounded by this plane. So if we let this point on the plane have coordinates x, y, z, we would want to maximize the equation where the volume is equal to x times y times z. The problem with this is a function in terms of three variables, and we need to determine a function in terms of two variables so we can apply our techniques for maximizing a function in terms of two variables. Well, in this problem, the plane x plus 3y plus 4z equals 12 is our constraint. So what we can do is solve this equation for a convenient variable, let's say x, then we can replace x with an equation in terms of y and z so that we have the volume equation in terms of two variables. So let's go ahead and do that. Again, we're going to take our equation for the plane and we'll solve it for x. So we'll have x equals 12 minus 3y minus 4z. And now we'll perform substitution into our volume equation. We can replace x with 12 minus 3y minus 4z, and that'll give us the function that we want to maximize. So we'll have the volume is equal to 12 minus 3y minus 4z times y times z. Let's go ahead and distribute here. So v of yz is going to be 12yz minus 3y squared z minus 4yz squared. Now in order to find the critical points for this function, we'll determine where both first partial derivatives are equal to 0 or undefined, and then we'll perform the second partials test to determine if we have a relative max, min, or neither. So let's go ahead and find the first order partial derivatives. So the partial derivative of v with respect to y would be 12z minus 6yz minus 4z squared. And the partial derivative of v with respect to z would be 12y minus 3y squared minus 8yz. And now our goal is to determine what values of y and z make both equations equal to 0 at the same time. So let's go ahead and take these two equations onto the next screen and see if we can solve this system. Let's start by factoring both of these equations. The first equation has a common factor of 2z. It'll leave us with 6 minus 3y minus 2z. And the second equation has a common factor of y. If we take a look at this first equation, one solution would be if z is equal to 0 and y is equal to 0. However, it's not possible for y and z to be equal to 0 because remember we're trying to maximize the volume, and if either y or z are equal to 0, the volume would be 0 and therefore not maximized. So what we're left with is trying to determine the solutions to the remaining factors. So now we have a new system to solve. We want to know when this inner factor is equal to 0 as well as this inner factor equal to 0. And this gives us a linear equation in terms of two variables, which we can solve using elimination or substitution. So now we want to determine when is 6 minus 3y minus 2z equal to 0, and when is 12 minus 3y minus 8z equal to 0. If we take a look at the y terms, they're the same, so I'm going to go ahead and multiply this first equation by -1. So if we multiply this first equation by -1, the y terms will be opposites, and they'll be eliminated. So let's go ahead and do that. So we're going to have -6 plus 3y plus 2z equals 0, and the second equation will stay the same. If the y terms go out, we're left with 6 minus 6z equals 0. this tells us that z would be equal to 1. Let's go ahead and determine the value of y by using this equation here. So we'll have 12 minus 3y minus 8 times 1, that'll be 8, must equal 0. So we have negative 3y equals, this would be positive 4. Move it to the other side, that's negative 4. So we have y is equal to 4/3. Let's also determine the value of x. Going back to the previous screen, remember that x is equal to 12 minus 3y minus 4z. So we have x equals 12 minus 3 times 4/3 minus 4 times 1. So we'll have 12 minus 4 minus 4. That'll give us x equals 4. So again, what this represents is what we think will be the coordinates on this plane that would maximize the volume with one corner on the plane and one corner at the origin. But to be sure, we really should show the second partials test where we determine the value of d and then make sure that d is greater than 0 and this second order partial is less than 0. Let's go ahead and do that now. Okay, so here are the first order partials that we found before. Now let's go ahead and determine the second order partials. The partial derivative of this with respect to y is going to give us negative 6z. The second order partial with respect to z would be negative 8y. And the mixed second order partial, we'll find the partial derivative of this with respect to z would give us 12 minus 6y minus 8z. And now we'll determine the value of d using these second order partials. Given x is 4, y is 4/3, and z is equal to 1. So the second order partial with respect to y, when z is 1, would be negative 6. The second order partial with respect to z is equal to negative 8y, and y is 4/3, so we'll have negative 32/3 minus the mixed partial when y is 4/3 and z is 1. It's going to give us 12 minus 8 minus 8. It's going to give us negative 4. This is going to end up being 64 minus 16, which obviously is greater than 0. So we have d is greater than 0. And the second order partial with respect to y, when z is 1, again is negative 6, which is less than 0. So d is greater than 0, and the second order partial is less than 0, which is what we were hoping for, meaning that those values for x, y, and z do maximize the volume. Let's go ahead and finish off by determining what that volume would be. Remember, the volume was defined by x times y times z. So we have 4 times 4/3 times 1. So the maximum volume would be 16/3 cubic units. Let's go ahead and finish by taking a look at that point in the plane. Here it is, and this is the location of the point where if we were to construct a box with one corner at the origin, it would produce the maximum volume. I hope you found this example helpful.